All right, we're looking at 9.3. We're going to talk about the effects of changing dimensions on area. So when we change the dimensions of a figure, how does that affect its area? So let's just start with this rectangle right here. We're going to find the area. Remember, the formula for area of a rectangle is just length times width. So in this case, we're just doing 8 times 4, which is 32. And this was in inches, so for area, that is inches squared. Remember, area is a two-dimensional measurement. Well, when we say it's 30, the area is 32 inches squared, that means if I divided this up into a bunch of squares, 1 by 1 inch squares, there would be 32 of them. Alright, what would happen if we changed one or both dimensions in this rectangle? So the original rectangle here, we had a width of 4 inches and we had a length of 8 inches, and we're going to make some changes to the length and width and see how that affects the area. So the original area was 32 inches squared, and we can just write that here on all of these. Alright, so let's see what happens if we make the width twice as long. So if it was originally 4, this would make it 8, and we make the length twice as long. So it was originally 8, so twice as long. 8 times 2 is 16. So that would give us a new length and width, length of 16, width of 8, and so we're doing length times width, and that would give us an area of 128 inches squared. So the question is, how does that compare to our original area? We can find out by taking our new area, dividing it by the original area, and 128 divided by 32 is 4. So by making the width twice as long and the length twice as long, we actually multiplied the area by 4. We quadrupled the area. Okay? Let's do a few more, and then we'll see if we can pick up on the pattern here. Alright, this time let's make the width twice as long, so it'll be 8. And let's make the length 3 times as long. So 8 times 3 is 24. So if we do our length times width, we get 192 inches squared. So once we double the width, triple the length, this is our new area. So let's take our new area, divide it by the original area, and see how many times larger it is. And 192 divided by 32 is 6. So by making these changes, we made the area 6 times as large. Okay, let's take the width and make it 4 times as long this time. Let's try another one. Let's make the length only half as long. So half of 8 would be 4. So we're going to do length times width. And that gives us a new area of 64 inches squared. So we're going to take our new area, divide it by our original area, and find out that that only makes it twice as long. Or excuse me, not twice as long, excuse me. Makes the area twice as much. So we have twice as many square units of area. Alright, last one, and then we'll try to see if we know the pattern. So the width is going to be 1/4 as long. So 1/4 of 4 would just be 1. And the length twice as long, so 2 times 8 is 16. And then we do our length times our width. We get an area of 16 inches squared. So we take our new area, divide it by the original area, and we find out that our area is now half the size that it used to be, based on those changes. And then from this, we're supposed to figure out a pattern. Supposed to see the pattern, see what is happening to the area each time based on these dimensions. And here's the pattern. Here we multiplied the width by 2 and the length by 2. 2 times 2 is 4. Here we made the width twice as long, the length 3 times as long. 2 times 3 is 6. 4 times a half is 2. 1/4 times 2 is a half. If you take the changes, what you multiplied each of the 2 dimensions by, and you multiply them, then that product tells you what we're multiplying the area by. Area is a two-dimensional measurement, so you're just multiplying those changes in each individual area, to find out what the change in the area is going to be. So I just kind of gave you our conjecture here. The product, so what we get when we multiply, the product of the change in each of the two dimensions equals the change in the area. So we just take the changes in each of the two dimensions, multiply them, and that tells us what the change in the area is going to be. So now that we know this, we don't have to go through this full process every time. Next time, if it says, hey, we're going to multiply the width by 2 and multiply the length by 3, I'm just going to say 2 times 3 is 6. I know the area is going to be 6 times larger, and I'll just take 32 and multiply it by 6, and that'll give me the new area of 192. So this was our learning process. We looked at all these examples so we could figure out the pattern. Now that we know the pattern, we can do things much quicker now. So let's turn the page. Let's look at example 2 here. The area of a triangle is 36 square millimeters. Suppose the height was 3 times as long and the base was 4 times as long. What would be the area of the new triangle? Notice they didn't even give me the actual height and the actual base, so it wouldn't even be possible to do the long method that we did on the table. But I know that area is always a two-dimensional measurement. And the two dimensions here are the height and the base. So the height is 3 times as long, it's being multiplied by 3. The base is 4 times as long, it's being multiplied by 4. So remember, if I take the change in each of the two dimensions and multiply them, I'll find the change in the area. So I know the area is going to be 12 times bigger. So if I want to find that new area, I just need to take the original area and multiply it by 12. So 36 times 12 is 432. And this was in millimeters. And so for area, that will be millimeters squared, because area is always two dimensions. It's always units squared. All right. If all of the dimensions in the figure are multiplied by the same number, then the new figure is going to be similar. Because if all the sides are getting multiplied by the same number, that means the sides will be proportional. And we have learned that similar figures have proportional sides. So on some of those examples we did already, the two dimensions were multiplied by the same number, but most of those examples had the different dimensions getting multiplied by different numbers. Okay, so those weren't similar figures. However, right here, we're going to focus on similar figures. So notice we're making the same change to each of the dimensions, and we'll figure out what happens when that's the case, because we can shortcut things just a little bit further. All right, so example 3, we're dealing with a triangle. It says it's a right triangle, so this is going to be the right angle here. Area of a triangle is 1/2 times base times height. The base and height are always perpendicular, so where this right angle is, those are your base and height. So 1/2 times 6 times 4 is 12. So the area of this triangle is 12 centimeters squared. So that is our original area that we're using. That's our original triangle. The base was 6 centimeters and the height was 4 centimeters. All right, let's make some changes and let's see what happens. All right, we're going to make the base and height both twice as long. So 6 times 2 is 12. 4 times 2 is 8. All right, so area is 1/2 times base times height. And that will give us 48 centimeters squared. Now, this is not disregarding what we've already learned. So you can come up with the answer here doing what we've already learned how to do. The new area is 48. We divide it by the original area. We find out it's 4 times as big. That's what you would get if you did exactly what we did earlier. 2 times 2 is 4. I know the area is 4 times as big. Let's check it out when we do it 3 times on each. So 6 times 3 is 18. 4 times 3 is 12. And we do our formula for area of a triangle. 1/2 times the base times the height. We should get 108 centimeters squared. So we take our new area We divide it by our original area, and we find out it's 9 times bigger, which is what we already talked about earlier. 3 times 3 is 9, so the area is 9 times larger. Last one, half as big. So half of 6 is 3. Half of 4 is 2. So we're doing 1/2 times the base times the height. And you should get an area of 3 centimeters squared. So our new area divided by our original area, and we find out our area is 1/4 of its original size. 1/2 times 1/2 equals 1/4. So the only real change here, because it's not a big change, the only real change here is that because these are the same numbers, when you take a number and you multiply it times itself, what we're doing is we are squaring that thing. We're squaring it. So instead of just saying we're going to multiply the change in each dimensions, we can say, because area is a two-dimensional measurement, it's units squared, whatever the change is to all the dimensions, we can take that number and square it. And I want to remind you that when we're dealing with similar figures, the number that you're multiplying all those sides by, the number that you're multiplying all the dimensions by, that is the scale factor. So in this example, the scale factor was 2. In this example, the scale factor was 3. In this example, the scale factor was 1/2. So the change in each dimension, which is the scale factor, that's what we're multiplying each dimension by, can be squared to find the change in the area. And this is only for similar figures. Only similar figures have a scale factor. But if you're dealing with similar figures, you're going to have a scale factor, and you can just square that scale factor to find the change in the area. Now, sometimes they'll tell you they're similar figures, and that's how you know all the dimensions are getting multiplied by the same thing. Sometimes they'll tell you that all the dimensions are getting multiplied by the same thing, and that's how you know you're dealing with similar figures. So we need to have a full understanding of that so we can take the information given to us and solve the problem. All right, so let's turn the page and let's look at these last couple examples. All right, the area of a square is 49 feet squared. Find the area of a square with sides 4 times as large. So if the sides are all going to be 4 times as large, that means our scale factor is 4. And we said we could square the scale factor to find out what happens to the area. So scale factor is 4, 4 squared is 16. So because all the sides are getting multiplied by 4, I know that the area is getting multiplied by 16. So I'm going to take the original area and multiply it by 16. So 784 feet squared, 16 times larger than the original area. All right, let's look at the last problem here. It says triangle ABC is dilated by a scale factor of 1/3. What is the ratio of the area of triangle ABC to the area of its image? Okay, so when you're dealing with dilations, the original figure is triangle ABC, and after you perform the dilation, then you get triangle A prime, B prime, C prime. Okay? And notice it says, what is the ratio of the area of triangle ABC to the area of triangle A prime, B prime, C prime? When it asks for a ratio, the order is important. When it asks for a ratio, the thing they mention first needs to go in the numerator, and the thing that they mention second needs to go in the denominator. Okay? Now, I don't have the actual areas to put in a ratio, so I can't figure it out that way. But I don't really need the actual areas. I just need to know how the areas compare. So like in this last problem, I know that the new area was 16 times larger than the original area. And I didn't need the 49 to do that part. All I needed was the scale factor. So right here, it says triangle ABC is dilated by a scale factor of 1/3. So remember, I can take that scale factor and square it, and that'll tell me what's happening to the area. So 1 squared is 1. 3 squared is 9. So this is what's happening to the area. Because all the sides are getting multiplied by 1/3, because that's the scale factor, the area is getting multiplied by 1/9. Now here's where some people might get tripped up, and they might circle this as the answer. this is what the area is getting multiplied by. If you multiply something by 1/9, it's going to get smaller, right? So what that means is the original area is 9 times larger than the new area. So pay attention to the order they wanted the ratio in. They want the area of the original triangle on top, and the area of the new figure in the denominator. Well, the original figure is the larger figure. It's 9 times larger. So for every 9 units of area in the original figure, we're going to have 1 unit of area in the new figure. So once you've squared that scale factor, just pay attention to the order that it wants that ratio of areas in. It may be that they want 1/9 as the answer. It may be that they want 9/1. It's either going to be this or its reciprocal that gives the proper ratio.